Hello. Today I want to talk to you about fire. Fire is something humans have been fascinated with for thousands of years. It's one of the first things our ancestors learned to control, and it changed everything about how we live. But have you ever stopped to think about what fire actually is? Why does it burn? Where does the heat come from? What are those flames you see dancing around? These seem like simple questions, but when you really dig into them, they take you deep into chemistry and physics and quantum mechanics. Fire turns out to be a window into understanding how atoms and molecules work, how energy is stored and released, and how the universe operates at the most fundamental level. Let me start with the most basic question. What is fire? Well, fire is a chemical reaction. Specifically, it's what we call combustion. When something burns, molecules in the fuel are combining with oxygen from the air, and this chemical reaction releases energy in the form of heat and light. That's what fire is. It's chemistry happening fast enough and hot enough that you can see it glowing. But this just pushes the question back a step. Why does this chemical reaction happen? Why does it release energy? To understand that, we need to talk about chemical bonds and energy. Everything around you is made of atoms. Your body, the air, the furniture, everything. And atoms can stick together to form molecules. When atoms stick together, we say they're chemically bonded. There are different types of bonds, but the basic idea is that electrons, the negatively charged particles that orbit around the atomic nucleus, get shared or transferred between atoms in ways that hold the atoms together. Now here's the key thing. Different arrangements of atoms have different amounts of energy. Some arrangements are more stable, lower in energy. Others are less stable, higher in energy. And nature tends to move from higher energy states to lower energy states when it can. That's the second law of thermodynamics showing up again. When you burn something, let's say wood or paper or gasoline, you're starting with molecules that are in a relatively high energy state. These molecules contain carbon and hydrogen mostly. When they react with oxygen, they form new molecules, carbon dioxide and water vapor, that are in a lower energy state. The difference in energy gets released as heat and light. That's fire. But wait, if the burned state is lower in energy, why doesn't everything just burst into flame spontaneously? Why is wood stable sitting on your table? Why do you need to light a match to start a fire? This is a very good question, and the answer has to do with what we call activation energy. You see, even though the final state, the burned state, is lower in energy, you have to get over an energy barrier to get there. It's like a ball sitting in a shallow bowl on top of a hill. The ball would have lower energy if it rolled down the hill, but it's stuck in the bowl. You need to give it a push to get it out of the bowl. Then it can roll downhill and release energy. The match provides that initial push. When you strike a match, friction creates heat. This heat gives some of the molecules enough energy to break their existing bonds and form new bonds with oxygen. This reaction releases more heat, which causes more molecules to react, which releases more heat, and you get a chain reaction. That's why fire keeps burning once you start it. The heat from the fire breaks bonds in the fuel molecules. The atoms rearrange themselves and form new bonds with oxygen. These new bonds are more stable, lower in energy, and the difference in energy comes out as heat. That heat keeps the reaction going by breaking more bonds in more fuel molecules. It's a self-sustaining process as long as you have fuel and oxygen. Now let me talk about what you actually see when you look at a fire. Those flames, those glowing colors, where do they come from? This is where we get into some beautiful physics involving light and quantum mechanics. When molecules react and release energy, some of that energy goes into making the products, the carbon dioxide and water, move very fast. Heat is just the random motion of molecules. Hot things have molecules moving faster than cold things. But some of the energy also goes into exciting electrons in atoms and molecules to higher energy levels. In quantum mechanics, electrons in atoms can only exist at certain specific energy levels. They can't be at just any energy. They have to be at particular discrete levels, like steps on a staircase, rather than a smooth ramp. When you put energy into an atom, you can bump an electron up to a higher level, but it doesn't want to stay there. It falls back down to a lower level, and when it does, it releases the energy difference as a photon, a particle of light. Different energy differences correspond to different colors of light. When you see a flame glowing yellow or orange or blue, what you're seeing is electrons in atoms and molecules being excited by the heat and then falling back down and emitting photons. The color tells you about the energy levels involved. In a typical wood fire, you see a lot of yellow and orange. This comes partly from glowing soot particles, tiny bits of carbon that get heated up until they glow. The color of a hot object depends on its temperature. This is called blackbody radiation, or thermal radiation. Something that's moderately hot glows red. Hotter, and it glows orange or yellow. Even hotter, white or blue. But there are also specific colors from excited atoms. Sodium, which is present in many materials, gives off a characteristic yellow color when excited. Copper gives green. Different elements give different colors. That's why fireworks can be different colors. They contain different elements that emit different colors when heated. The blue you sometimes see at the base of a flame, like in a gas stove, is different. That's coming from excited molecules, particularly excited carbon dioxide and water vapor, emitting specific wavelengths of blue light. The blue indicates that the combustion is more complete, burning hotter and more efficiently. That's why a blue flame is hotter than a yellow flame. Now let me go deeper into the chemistry. What exactly happens when a hydrocarbon, like wood or gasoline, burns? Let's take something simple, like methane, which is natural gas. Methane is one carbon atom bonded to four hydrogen atoms, CH4. When methane burns, it reacts with oxygen. The complete reaction looks like this. One molecule of methane plus two molecules of oxygen produces one molecule of carbon dioxide plus two molecules of water and releases energy. CH4 plus 2, O2 makes CO, 2 plus 2, H2O plus energy. But what's actually happening at the molecular level is more complicated. The bonds in methane and oxygen have to break, then new bonds have to form. Breaking bonds requires energy. Forming bonds releases energy. The reason combustion releases energy overall is that the bonds in carbon dioxide and water are stronger, more stable, than the bonds in methane and oxygen. The energy you get out from forming the new bonds is more than the energy you put in to break the old bonds. The details of how this happens involve a lot of intermediate steps and what we call free radicals, highly reactive molecules that have unpaired electrons. The fire is full of these reactive species bouncing around, reacting with each other, breaking bonds, forming bonds. It's a chaotic molecular dance. One important radical is the hydroxyl radical, OH. This is very reactive and plays a key role in combustion. There are also radicals like CH3 and various others. These radicals propagate the chain reaction. One radical reacts to create more radicals, which react to create more radicals, and the whole thing cascades. That's what makes fire spread. Now, why does fire need oxygen? Can't you burn things without it? Well, combustion, as we normally think of it, requires oxygen because oxygen is very good at forming stable bonds with carbon and hydrogen. Oxygen is what we call electronegative. It really wants to grab electrons from other atoms. When it bonds with carbon or hydrogen, it forms very stable molecules, CO2 and H2O, and releases a lot of energy. But there are other reactions that look like fire but don't use oxygen. For instance, If you burn hydrogen and fluorine together, you get a flame, and no oxygen is involved. Fluorine is even more electronegative than oxygen. It grabs electrons even more aggressively. But for most everyday fires, oxygen from the air is the oxidizer. Interestingly, oxygen makes up about 21% of the air. If there were more oxygen, fires would burn much more intensely. If there were less, fires would be weaker or wouldn't start at all. There have been periods in Earth's history when oxygen levels were higher, and we think that led to much larger and more intense wildfires. The amount of oxygen in the atmosphere is actually controlled by a balance between photosynthesis, which produces oxygen, and various processes like combustion and respiration that consume it. Let me talk about the different stages of fire. When you first light something like a piece of wood, you're heating it up. At first, the heat drives off water and other volatile compounds. This is why wet wood is hard to burn. You have to evaporate the water first, and that takes energy. As you keep heating the wood, you start to break down the complex molecules that make up the wood, things like cellulose and lignin. This process is called pyrolysis. The heat breaks these big molecules into smaller ones, creating flammable gases. These gases mix with oxygen and ignite, creating the flames you see. What's left behind after the gases have been driven off is mostly carbon, what we call charcoal. This carbon can also burn, but it burns differently. It glows but doesn't produce much flame. That's because solid carbon reacts with oxygen more slowly than the gases do. The combustion happens right at the surface of the solid, creating a glowing ember. Eventually, all the carbon gets oxidized to carbon dioxide, and you're left with ash. The ash is the minerals that were in the wood, things like calcium, potassium, and other elements that don't burn. They just remain behind as a white or gray powder. Now, let me address something that confuses a lot of people. When you burn something, where does the mass go? If you start with a piece of wood and you burn it, you end up with a little bit of ash. The wood seems to have disappeared. Did the mass get destroyed? Number. Mass is conserved. This is a fundamental principle. The mass of the ash plus the mass of the gases that were released, the carbon dioxide and water vapor, equals the mass of the wood plus the mass of the oxygen that was consumed. Nothing was destroyed, it just changed form. The solid wood and the gaseous oxygen became gaseous carbon dioxide and water vapor, which floated away, plus a bit of solid ash. In fact, if you could capture all the products of combustion, the gases and everything, and weigh them, they would weigh more than the original wood, because you've added the mass of the oxygen from the air. People didn't understand this for a long time. Before the discovery of oxygen and the understanding of combustion, people thought burning destroyed matter. It was Lavoisier in the late 1700s who really figured out what was happening and established the law of conservation of mass. There's also conservation of energy. The energy released as heat and light was already there, stored in the chemical bonds of the wood and the oxygen. When those bonds rearranged into more stable configurations, the energy was released. Energy isn't created or destroyed, just transformed from one form to another. Let me talk about some special types of fire and what makes them different. A candle is interesting. The solid wax doesn't burn directly. Instead, the heat from the flame melts the wax near the wick. The liquid wax gets drawn up the wick by capillary action. At the top, the heat vaporizes the wax, turning it into a gas. It's this wax vapor that actually burns, combining with oxygen in the air. The flame has different zones. The innermost part, right near the wick, is relatively cool and doesn't have much oxygen. This is where the wax is vaporizing. You can actually see it's darker there. Then you have the bright glowing part of the flame, where the combustion is happening. And at the very outside, the flame is hotter and more blue. where there's more complete combustion with plenty of oxygen. If you put a piece of paper in the middle of a candle flame, where it's not as hot, the paper might not catch fire. But at the edge of the flame, where it's hotter, it will. This shows that the flame isn't all at the same temperature. A gas stove is different. The gas, usually natural gas, which is mostly methane, mixes with air before it burns. That's why there are little holes in the burner where air gets drawn in. This premixing allows for more complete combustion, which is why you get a blue flame instead of a yellow one. Blue means hotter and more efficient. In an oil lamp or a kerosene lantern, liquid fuel gets drawn up a wick, vaporizes, and burns, similar to a candle. The design of the lamp, with its glass chimney, creates a draft that pulls air through, providing oxygen and making the flame burn steadily and brightly. Forest fires are combustion on a massive scale. They work on the same principles, but there are complications. The fire creates its own wind patterns as hot air rises and cooler air rushes in to replace it. This can make the fire spread faster. The heat from the fire can dry out vegetation ahead of it, making it easier to burn. Forest fires can even create their own weather, with fire tornadoes and thunderclouds forming from the rising heat. Now let me talk about what happens at the atomic and molecular level in a bit more detail, because this is where the real beauty of fire emerges. When molecules collide, and they're moving fast enough because they're hot, they can break apart. The bonds between atoms get stretched and can snap. A chemical bond is fundamentally an electromagnetic phenomenon. It's electrons being shared or exchanged between atoms in a way that reduces the overall energy. The mathematics of this comes from quantum mechanics. You have to solve the Schrödinger equation for multiple atoms together to figure out how the electrons arrange themselves. What quantum mechanics tells us is that when atoms come together, their electron orbitals overlap and combine to form molecular orbitals. Some of these molecular orbitals are lower in energy than the atomic orbitals, and these are called bonding orbitals. Electrons in bonding orbitals hold the molecule together. Other molecular orbitals are higher in energy, and these are antibonding orbitals. Electrons in antibonding orbitals push atoms apart. In a stable molecule, more electrons are in bonding orbitals than in antibonding orbitals, so overall there's a net attractive force holding the atoms together. But this bond has a certain strength, a certain amount of energy holding it together. If you put in enough energy by heating the molecule or hitting it with another fast-moving molecule, you can break the bond. In a fire, molecules are constantly colliding, breaking apart, and forming new combinations. The heat provides the energy needed to break bonds. Then the atoms recombine in new ways, forming more stable molecules and releasing energy. Some of this energy goes into heat, making the products move faster. Some goes into light, exciting electrons and creating photons. And some goes into breaking more bonds, keeping the reaction going. The question of why some molecules are more stable than others, why carbon dioxide is more stable than methane and oxygen, gets down to the details of how electrons arrange themselves in molecules. It's all quantum mechanics. The electrons find configurations that minimize the total energy of the system, taking into account the attraction between electrons and nuclei, the repulsion between electrons, and the quantum mechanical requirement that electron wave functions have to fit together in certain ways. I could write down the equations, the Schrödinger equation for a molecule, but solving them exactly is impossible for anything bigger than the simplest molecules. Instead, chemists use approximations and computers to calculate molecular energies and predict which reactions will happen and how much energy they'll release. One beautiful thing about fire is that it's visible chemistry. Most chemical reactions happen invisibly, too small to see, too slow to notice. But fire is dramatic. You can see it, feel it, hear it. It gives you a direct sensory experience of molecules rearranging themselves, of chemical energy being released. And fire has been crucial to human civilization. Cooking food made more nutrients available and made food safer by killing bacteria. Fire kept us warm, extended the day by providing light, protected us from predators, and allowed us to shape tools by heating metals. The control of fire was probably one of the most important technological advances in human history. Later, we learned to use fire in more sophisticated ways. Steam engines use fire to boil water, creating steam that drives pistons or turbines. Internal combustion engines use fire, small controlled explosions of gasoline or diesel, to drive pistons that turn wheels. Rocket engines use fire, burning fuel and oxidizer at incredible rates to produce thrust. Most of our electricity comes from fire, burning coal or natural gas to heat water and drive turbines that turn generators. Even your own body uses a form of controlled fire. When you eat food, your body breaks it down and combines it with oxygen in a process called cellular respiration. This is chemically similar to combustion. You're oxidizing the carbon and hydrogen in food to produce carbon dioxide and water and releasing energy. The difference is that instead of happening all at once and producing heat and flames, it happens in many small steps, controlled by enzymes, and the energy is captured in molecules like ATP that the cell can use. But fundamentally, it's the same chemistry. You are a slow, controlled fire. Now let me address a question that children often ask. Can you have fire in space? Well, it depends on what you mean. If you're in the vacuum of space, with no air, you can't have fire in the normal sense because there's no oxygen. But if you bring your own oxygen, you can have combustion. Rocket engines work in space by carrying both fuel and oxidizer. The space shuttle's main engines burned liquid hydrogen and liquid oxygen, even in the vacuum of space. Fire behaves differently in microgravity, though. On Earth, hot air rises because it's less dense than cold air, and this creates the characteristic flame shape, pointing upward. In microgravity, there's no up or down, no convection. A flame becomes spherical, expanding outward in all directions. And without gravity-driven convection to bring in fresh oxygen, the flame can smother itself in its own combustion products. Flames in space tend to be dimmer and bluer than on Earth. There's also the question of fire underwater. Can you have fire underwater? Generally no, because water prevents oxygen from getting to the fuel. But there are some materials that burn underwater. Magnesium, for instance, burns so hot that it can decompose water molecules, using the oxygen in the water itself to keep burning. That's why you can't put out a magnesium fire with water. Some naval flares use magnesium for this reason. Let me also mention that not all light from hot things is fire. If you heat a piece of metal until it glows, that's not fire. That's just thermal radiation, the metal getting so hot that it emits visible light. There's no chemical reaction happening. Similarly, lava is not fire. Lava is molten rock, and it glows because it's hot, but it's not burning. There's no combustion reaction. Real fire requires a chemical reaction. The heat and light come from the energy released by the reaction, not just from something being hot. Though I should say, the distinction can get blurry. In a very hot fire, some of the light is coming from soot particles that are glowing just because they're hot, which is thermal radiation, and some is coming from excited atoms and molecules, which is chemiluminescence. Usually it's a mix of both. There are also cold flames, which is a fascinating phenomenon. Under certain conditions, usually low pressure, you can get combustion reactions that happen at relatively low temperatures, around 300 to 400 degrees Celsius, instead of the usual 1000 or more. These cold flames are dim, often invisible to the naked eye, and they involve different chemistry with more complex intermediate species. They're important in understanding combustion in engines. Another interesting thing is spontaneous combustion. Can things really burst into flames by themselves with no external spark? Yes, under the right conditions. If you have a material that can slowly oxidize, like oily rags or hay, and it's in a confined space where heat can build up, the slow oxidation can generate heat. If the heat can't escape, the temperature rises, which makes the oxidation go faster, which generates more heat, and you get a runaway process that eventually reaches the ignition temperature. Then you have fire. This is why you shouldn't pile up oily rags in a closed container. It's why haystacks can spontaneously combust if they're too large and too wet. The wet hay ferments, which generates heat, and if the heat builds up enough, it can start a fire. Let me come back to the fundamental question. Why does fire burn? I've told you about the chemistry, about bonds breaking and forming, about energy being released. But there's a deeper question. Why is this the way the universe works? Why do atoms form bonds? Why do some arrangements have less energy than others? The answer goes down to the fundamental forces of nature and the laws of quantum mechanics. Atoms form bonds because of the electromagnetic force, the attraction between positive nuclei and negative electrons. The specific way bonds form, the specific energies involved, these all come from solving the equations of quantum mechanics. And why are the laws what they are? Why does the universe follow these particular mathematical rules? I don't know. Nobody knows. That's where physics reaches its current limit. We can describe how the universe behaves with incredible precision. We can make predictions that match experiments to many decimal places. But why the universe follows these laws and not some other laws, that's a question we can't answer. Maybe someday we'll have a deeper theory that explains why the current laws have to be the way they are, or maybe the laws are just arbitrary, an accident, and in other universes with other laws, physics works differently, and there's no fire at all. We don't know. But what we do know is beautiful and deep. Fire, this everyday phenomenon that humans have been using for hundreds of thousands of years, connects to the deepest levels of physics and chemistry. Understanding fire means understanding quantum mechanics and electromagnetism and thermodynamics. It means understanding how energy works, how atoms bond, how reactions proceed. Every time you light a match or watch a campfire or turn on a gas stove, you're witnessing quantum mechanics in action. You're seeing electrons rearranging themselves, finding lower energy configurations, emitting photons as they drop down to lower energy levels. You're seeing the second law of thermodynamics as energy disperses and entropy increases. You're seeing chemistry happen in real time, and I think that's wonderful. The universe is comprehensible. We can figure out how it works. A child's question, why does fire burn, leads you to some of the deepest and most beautiful parts of science. That's what I love about physics. The simple and the profound are connected. The everyday and the fundamental are the same thing, just viewed from different perspectives. So the next time you see fire, remember, you're not just seeing flames. You're seeing quantum mechanics. You're seeing the electromagnetic force in action. You're seeing energy that was stored in chemical bonds being released into the universe. You're seeing atoms dancing their eternal dance, following the mathematical laws that govern everything from the smallest particle to the largest galaxy. And that, I think, makes fire even more magical than any ancient myth. The truth is more amazing than we could have imagined. Thank you.